Alright, welcome everybody. So today we're gonna start with first the language of first order logic. So first order logic is strong enough to develop all of mathematics. It's much stronger than sentential logic. Still, as we're gonna see, it's not super complicated. This language is not that complicated. Still, but it's not restrictive at all in the sense that one can develop all mathematics. One can write every mathematical statement in this language if you're in the right setting. Like for instance the setting of set theory. So today we'll just start with describing what the language is, and as you see, it's quite simple. Alright, so we need to define two things to develop a language. One is the symbols, and the other one is how to put the symbols together. Right, so our expressions are going to be nothing else but strings of symbols. Like when you write on a computer, and you have an email is a string of characters, or a program is a string of characters. So our mathematical expressions are going to be also strings of symbols, and that we can only put together according to certain rules, like the same as in English. Alright, so let's start with the symbols. Okay, so let's slowly go through the symbols that we have, and then we'll move on to explain how you put them together. Okay, so there are different kinds of symbols. So first come the logical symbols. And there are a few of them. The logical symbols are always included in first order logics. First one is the symbol for equality. Some people don't put it, but yes, we're going to always consider equality. The equality symbol that you guys, I assume, know very well. Then come the connectives that have their logical meanings. Let's write down what they are. So this one is and, this one is or, this one is if and only if, this one is implies, this one is not, for all, and that exists. Those are our logical symbols. Then come the variable symbols. So we're gonna be able to use variables in our formulas. The variables, formally we call them v0, v1, v2, v3, v4, and we can use as many variables as we want in each formula, finitely many in each formula, but overall depends, we can choose as many formulas as we want. In general, we are going to use, just because visually it looks better if we use variables x, y, z instead of v0, v1, v2, it's all like a lot of v's together. But formally we think that we are using this v0, v1, v2. Okay, equality, connectives, variable symbols, what else? We have punctuation symbols. We're only going to use the parentheses. So the left parentheses and the right parentheses are characters that can show up in our formula, and they are only going to help us to be able to parse the formula, to like read it and understand, and not to get confused about how to read the formula. Okay, so these are the logical symbols. They are in all settings whenever you're in first order logic. And then come the vocabulary symbols. The vocabulary symbols, they vary according to the situation. So it depends what you're working on. You can have different vocabulary symbols. Alright, so they are not always the same. Let's just view a few examples of settings. So for instance, if you're talking about groups, you have usually three symbols. One for the E for the identity, multiplication or addition, or just sum of the operation symbol. Here I'm putting star, and a unary operation that takes an inverse, takes an element and maps it to the inverse. In a group, you always must have inverse, right? So you can talk about groups in this vocabulary. If you want to talk about fields, then you might use the vocabulary 0, 1, plus, and times. That's appropriate for fields. If you want to talk about arithmetic, like the natural numbers, for instance, if you're talking about the natural numbers, you might want to add less than or equal, right? So on the natural numbers, you talk about 0, 1, plus, times, less than or equal, and with that, you can pretty much say everything you want about the natural numbers. In set theory, where you can actually develop all of mathematics, you only need one symbol, and that's the symbol for belongs, and from that you're gonna build everything else. So alright, so different settings, we have different vocabularies. In set theory, if you want to develop all of mathematics, then set theory is the place for you, and that's where you only use this symbol and develop all the rest. But sometimes you want to analyze, let's say, the natural numbers and how difficult it is to prove things in the natural numbers, and then you will work in this setting, which is more restrictive than all of mathematics, but still good enough to say quite a bit. And then if you want to work on these settings, in these two settings, or many others, in particular algebraic structures, that's not because you want to develop all of mathematics, but essentially because you want to understand the logical properties of certain types of structures, which that's what an area of logical model theory does. You look at particular kind of structures and understand the algebraic properties through the eyes of logic. Okay, so there are three types of vocabulary symbols. Let's go through them one by one. So we have the C's are called the constant symbols. The constant symbols, they represent elements. Like for instance, in our examples, like E, the identity in the group, 0 and 1, they are constant symbols, all right? So they represent constant elements in whatever structure you're working with. Okay, so then after constant symbol come these function symbols, and the function symbols represent operations. So in these examples, for instance, the multiplication operation for the group and the inverse operation of the group are function symbols, and so are plus for the natural numbers and times for the natural numbers. They are operations. They take elements and give elements out. All right, so for instance, plus operation takes 2 elements and gets 1 element out. But the inverse operation takes 1 element and gives you the inverse out. All right, so functions, they don't need to be from 1 element to 1. They can take many elements and give you 1. And there are examples where you may have like 3 inputs and then output 1. That's also allowed. And then we have relation symbols. Relation symbols represent properties of tuples. For instance, in our examples, less than or equal and belong are relation symbols. All right, so relation symbol means like you're given a tuple, like let's say 2 natural numbers. If you write that a number is less than or equal another one, you're gonna get that that's either true or false. Okay, so relation symbols don't return objects, but return kind of true or false, right? So you apply 2 objects, 2 elements, and then something, and then you see whether this holds or not. The same with belongs. No, is this element a member of this element, true or false? All right, so that's the difference between relation symbols and function symbols. Functions return objects, relations return trues or false. Let's notice that so both function and relation symbols can take arbitrary numbers of inputs, but each symbol has a fixed additive. All right, so each symbol takes a fixed number of inputs. For instance, plus always takes 2 inputs, right? You cannot do plus of 17 inputs. I mean, you have to do many pluses if you want to do 17. So just a symbol plus only takes 2. If you do the inverse of an element, that only takes 1. So if you're gonna do less than or equal, that takes 2. And that's called the additive of the symbol. Each symbol comes associated to an additive that tells you how many elements you can use it for. 2 things to emphasize. Here the ... It means that we can have an arbitrary number of constant symbols, arbitrary number of function symbols, arbitrary number of relation symbols. We may have 0, 1, 2, any number. We may have infinitely many of each of them. That's fine. That's legal. That's fine. Like as we see in the examples, in all of them we have different numbers of symbols. Another thing to observe is that all these symbols right here, they are nothing but symbols. So far, they don't have a meaning until we give them a meaning with axioms. Right at the beginning, all they are is symbols, and if you're a binary function symbol, you're gonna be applied to 2 elements. But what you do in those 2 elements, you don't know. The symbol doesn't tell you anything about what to do with the elements. It's just a symbol that you apply to elements. All right. So the symbols at the beginning, they have no meaning. Right. So far we're gonna formally look at the language without looking at the meaning of the symbols. And then we're going to see how, once you have a vocabulary set up, you can assign different meanings to the symbols of the vocabulary. But that comes later. So first, we just look at it look at them without meaning. Okay, so let's now take a look at how is that we build these expressions for the language using these symbols, all right? So we're gonna have two types of expressions that we can build with the language, and there are gonna be terms and there are gonna be formulas, all right? So both are gonna be strings of symbols, but the terms are gonna represent elements, and the formulas are gonna represent statements. They could be true or false, all right? So for instance, a term is gonna be something like 1 + 1. That's a term. It represents an element, all right? And a formula is gonna be something of the form 1 + 1 less than or equal 0 or x equals y. That's something that is either true or false, right? So the top ones are terms, they represent elements. Bottom one is formulas, they represent statements. Okay, so let's see how we build them little by little. Okay, so a term is going to be everything that can be built according to the following rules. First, all the constant symbols by themselves, they are terms. Okay, so 0, 1 by themselves, they are terms. They represent elements, so you can put them by themselves and they are terms. And also, I guess E in the previous example, also a term. Variable symbols, also, you can put a variable symbol by itself and it's a term. It's representing an element. We don't know what the element is because it's a variable, but still, it's a term, all right? So it's representing an element, not a truth value. Okay, so we can just put the variables by themselves, and then we can build from them using the function symbols. Okay, so here is a formal way of saying how you do this. If you have built terms already, like T1, Tn, these are terms that you have built already, then you can apply, and you have an n-ary function symbol, meaning a function symbol that takes n input, like in this case fi. Then you can build a new term by putting the fi, the symbol for fi, then parentheses, then T1, then comma, dot dot dot, well then T2, then T3, put all of them together, then Tn, and then close the parentheses. Okay? So that is how you build a symbol. For instance, suppose we have a variable, if we say a variable symbol is a term, and a constant symbol is also a term, and we can put essentially plus of these two, and we will have a term. That's what we usually write as v2 plus 0, and that's how we can actually write it. But for now, we're looking at it formally, we write it like that. Plus applied to these two elements, v0 and v2 and 0. All right, and then once we have that, that's a term already. So if you have another term by itself, we can apply an operation to these two terms, and then we will have that. Okay, and then we can keep on building. Now we can have like times 1 comma 1, that's another term, and we can put these together with another operation, let's say times. And then if you have all of these, suppose we have an inverse symbol, we can take all of these and apply the inverse, which one will write there, but the way we are doing it right now, we shouldn't write it there. Oh, let me erase. We should write it -1 up here, apply to everything. All right, so again, this is not the way we're gonna write it usually, but that's the way, the formal way. Okay, so you can build terms by applying function symbols to previous terms. By applying here, I don't mean applying anything, because these are just symbols. So what I mean is just you put the symbol for f right here, you put the symbol for parentheses, then you put all the symbols that correspond to the first term, you put a comma, then all the symbols for the second term, put a comma, so on and so forth, up to the nth term, and then you put the symbol for parentheses, and then you end up with a long string, right? So we are not applying anything. This has no meaning. It's just a string of characters, and that's how we build terms. Later, terms are gonna represent elements. Okay, so then come the formulas. The formulas now represent statements, which are going to be either true or false when we interpret them later. So far, it's just strings of symbols again. And then there are a simpler kind of formulas called the atomic formulas, which we build first, and then we're going to build all the formulas. So what are the atomic formulas? Atomic formulas come in two kinds. The simplest one is a formula of the form T1 equals T2, where T1 and T2 are, these two guys are terms that we built before, right? So these are terms that they were built before, and now we put an equality between the two terms, and now we have an atomic formula that could be either true or false, depending on how you interpret the terms. So that's one term, and another term is when you apply a relation symbol. This is a relation symbol from the previous slide to a bunch of terms, okay, that you built before. So you have an n-ary relation symbol. That means that the relation symbol takes n inputs, and what you do is you put the symbol for the relation, parentheses, then the symbols for the terms, one after the other, and then close parentheses. Okay, so that's how you build atomic formulas. Let's do an example. Let's cross this out. Let's cross this out for now because we don't need it. So an example for this, for instance, let's suppose we have a term 1 plus 0 and another term 1 plus 1, and these are two terms. Well, in reality, these are not terms. Maybe let's write them correctly. What I mean here is plus 1 comma 0 plus 1 comma 1. That should be the right way of doing it. And then between these two terms, we can put, let's say, the equality symbol. Or instead, we could apply a relation symbol. For instance, we could write 1 minus 1 less than or equal 1 plus 1, right? And now this is not a, now we have a statement. This is 1 plus 1, 1 minus 1 less than or equal 1 plus 1. The right way of writing this again would be, according to this notation, less than or equal applied to these two terms, first term and second term. Okay, so the bottom one, this one is the formal way of doing it, but it's not the nice way. Okay, so that's how you build atomic formulas. From the term, you apply relations to the terms. Essentially, here equality is behaves like a relation, right? So it's like a binary relation. Okay, so from the atomic formulas, now we're gonna build all formulas. So how do we build the formulas? First, all the atomic formulas are formulas. We start with those. So those are formulas. They are just a special kind of formulas. Okay, and now we're gonna start building formulas from previously built formulas. So if you have a formula phi that we built already, we can put the not symbol up front, and we have a new formula. Okay, just put the not symbol up front. This is similar to sentential logic, by the way, that the not and the second line. If you have formulas phi and psi that you have built already, then from those you can build a bunch of formulas. Phi and psi, phi or psi. Phi implies psi, phi if and only if psi. Okay? And in all of them, we're putting parentheses in the outside so that it doesn't get confused when we apply another, when we put another connective next to them. Okay? So later, some people have rules of when you can omit parentheses and not omit parentheses to simplify reading. Formally, we just put them every single time. But in reality, we don't need to put them every single time. But for the language, let's put them every single time. And you can also build formulas by putting a for all or exist up front and a variable. This here and this here is a variable symbol. For instance, let's look at some examples that we had before. So we had that the variable by itself is a term and a constant by itself is a term. We can put a relation symbol, and now we have an atomic formula, okay? And then we can build another atomic formula right here. Now we have two atomic formulas, and now we can put them together, and we can write this one and this one. And now we have a composed formula. And then maybe we write another formula right here, 1 less than or equal 0, and then we put them together. Well, when we put this together, and we need to put the parentheses before, now we put this together, let's say we put implies. And now we build a new formula, okay? And now we keep on growing by building new formulas like that, all right? So if and only if 1 inverse equals 1. What I just wrote makes no sense. And then we can put quantifiers up front. So we can say for every v, this holds. And v is a variable symbol. I should have put like v1 if they want to be formal. Now we have a more composed formula, and then I can say for x that exists v2 such that blah blah blah. v2 doesn't show up, doesn't matter. This is still a legal formula. Okay, so that's how we build formulas from the bottom up. See you guys next time.